Alright, today we're talking about simple harmonic motion. Simple harmonic motion can be seen in nature in many ways. One simple way of seeing it is what's called the pendulum. You take a ball and you attach a string to it, and you just hold the ball up on your string and you push it to the side, let it swing back and forth. That's simple harmonic motion. We call that a pendulum, or simple pendulum. The first thing we're going to talk about today is what happens if you have a box that's attached to a spring. And the type of motion that we're going to talk about here, it exists all around us, inside of a quartz watch, inside of a grandfather clock, inside of, in a way, atomic clocks. Probably not really atomic clocks, but simple harmonic motion describes repetitive motion, periodic motion, motion that repeats itself and has a pattern to it that we can describe. And that's what we're going to talk about today. So let's get right to it. Alright, so the system that we're going to look at first is going to be basically a box attached to a spring. And I want to do is like no, not that one. Look at this. Okay, so this is going to be a surface, and there's going to be a rigid wall. Okay, so this is a fixed. This over here is some kind of rigid fixed wall. This is just a wall. And attached to this wall, we're going to have a spring. Okay, so here's our spring. And the spring can basically do two things. It can compress, and it can stretch. And it's going to be what we call a Hooke's law spring. So we're going to have a mass M here. We're going to have a spring that has a spring constant K. It's not really writing like it normally does. I must have some different setting on here. I don't know. Normally the letters look better than this. I don't know what's going on. It's weird. Anyway, so the pointer looks different too. Huh. Okay, so mass attached to a spring, right? It's what we call a Hooke's law spring. And that is that a spring such that it has what we call a restoring force, F sub s, the force of the spring, that's equal to negative k multiplied by x. Oh. Something's wrong with my tablet. Some of the settings that I put on it aren't working anymore. I wonder if... Huh. Okay, well, that's fine. I'll just work with it. I don't know what I did differently. Alright, Hooke's law spring. Force equal to negative kx. What that means is that if I take this same system that I have right here and redraw it in a different position, so if I take this shape, and we just make that black again. Let's say that we stretch this spring out a little bit, right? So let's say the spring stretches out to a new position. Let's say it stretches out kind of like this. So the spring's a little bit looser now, and it's attached still to a box. So now let's say that we push our box to a new location. All right, it's a box. It should be off. It's just a flat box. There's another one thing we have to say here, which is that the surface is going to be frictionless. If you stretch the box, all right, and let's say that we identify that this position right here is going to be called x. Oh, what was that? Oh boy, what are we doing here? Crashed. Okay. I wonder if I need to restart my computer for this. I don't know. Alright, let's see what happens. Where'd my pen go? Right. So let's say that we call this position right here. We're going to call that position x equal to 0. X equal to 0. And then when we have the object pulled out to some point, we'll just call that distance from there out to there, we'll call that x. And that's going to go basically to the center of the box. Okay? we pull it out to that distance, then what we can say is there's going to be a force acting on this box, and the force is basically going to act back this way. That's going to be our spring force. So basically, when x is a positive quantity, the spring force is going to be negative. When x is a negative quantity, such as when the box is pushed to the left or is in a position somewhere over here, the spring force is going to act to the right, and we can draw another picture of that too. So if we take our, if our system was in a different situation here, like for example, if the box was having some negative x value to where the spring was like really crunched up right here, because the spring can basically be compressed and stretched. So now if our box is right here, then now we would have x be negative. Okay, so this distance from here, let's do this. Think about it like this actually, what's the easiest way to do this? We basically just have, this is positive x direction, and that's negative x direction, right? So if I have the box here, then I have an x coordinate right here. You know, for example, the x coordinate here could be like negative 3 centimeters, right? And the x coordinate here could be like, I don't know, x equal to positive 2.5 centimeters or something like that, right? And the quantity k, just to remind you, k is what we call spring constant. Okay? And the spring constant is expressed in newtons per meter, so the unit for this would be like newtons divided by meter. So if, you know, example, if it was like 200 newtons per meter, to every meter you stretch it, you get a force of 200 newtons. So the force here, if x is negative, the force is going to push back this way. That would be the direction of the spring force. So this is the type of system that we want to analyze here, basically. Okay? This is the type of system that we want to analyze. In particular, what we want to analyze is what happens if I take this box, I stretch it to some position, and then I let it go. And I allow it to just, what's it going to do? If it's a frictionless surface and I stretch the box to some position like right here, it's going to feel a force back in that direction, right? It's going to feel an acceleration in the same direction. And we can even label on here that there's going to be, at this location, there's going to be an acceleration back this way. That's the direction of the acceleration here. When the box is in this position, the acceleration is going to be directed this way. Okay? Because if there's a force, there's also going to be an acceleration. And everything just looks bad today, and I apologize for that. Something's different about the way that this is interacting with my tablet. I don't know what it is. It's like the driver's gone or something. Okay, whatever. Point is, force this way, acceleration this way, force this way, acceleration to the right. And what we want to do is we want to think about what's going to happen if we let this system just move forever. If there truly is no friction here, yeah, it looks okay, but like, okay, as long as you guys can follow it, that's alright. It's just going to be a little sloppy today. So, think about what's going to happen here, right? You pull the box to some location, you let it go, and it's just going to oscillate back and forth and back and forth and back and forth and back and forth forever. Forever. Because as long as the spring is some kind of a perfect spring that doesn't heat up in any way, and as long as the surface is frictionless, and this is all completely imaginary, then the system's going to oscillate back and forth over time, right? And that type of motion is what we call simple harmonic motion, where the object basically goes back and forth and back and forth, all right? And to understand how this works, what we want to do is we want to relate the position of the object to its acceleration, and we want to use that to basically ask the following question. Suppose that we know something about where the system starts. Can we describe what the position as a function of time is? And can we describe what the velocity as a function of time is for the system? That's basically what we want to be able to understand here, is what we call the equations of motion. The position is a function of time and the velocity is a function of time for an object that oscillates back and forth and back and forth. We'd also like to know how frequently it does this. So that would be like finding the period of the motion or the frequency of the motion. These are the kind of things that we want to analyze for a system like this. And we can fully describe all these things very well. And it's pretty simple once we understand it. So let's get to it. So let me give you another setup of this same system here, okay? Let's suppose that we have the following initial conditions, okay? So we take our system, right? Yeah, let's make it black. Let's actually use like a box, put it right there, make it red. And then let's use, what's a good thing to use for a spring that won't look like junk? I guess we'll just keep using sometimes you'll see the springs just drawn with jagged arrows, like, just go like this. This just looks so bad.
got your spring. There it is. A little long, weird-looking spring. Okay. And let's say that this position right here we define as x equal to 0. Okay, so this is going to be x equal to 0. And let's say this is what we do. We bring the object out to a position that we call x equal to a. That's our starting position, okay? That's our starting position, x equal to a. Now the letter a is going to stand for something that we're going to use a lot with this, so we're going to call that amplitude. This is a type of maximum displacement, or max position, you might say. Let's call it max position. Amplitude is maximum displacement. Okay. And we're also going to say that the initial velocity of this object right here, v initial, is going to be equal to 0. And really the way I want to write that is that the velocity at time equal to 0 is 0, or v naught is 0. So basically we stretch the box out, we release it from rest, right, and it starts to move. Yeah? It moves under the subject of a force that goes this way, and it has an acceleration in that same direction, right? So that's our system. And what we know about systems like this is if you have an object with mass m subject to only one force F, then what we can say is that if I sum, oh my god, just undo like by doing that, I guess. If I take the sum of all forces acting on my object in the x direction, it should be equal to the mass of the object multiplied by its x acceleration, right? And in this case, this is going to be an acceleration in the x direction. The left-hand side, all we have is this spring force, right? And we said before that the value of the spring force is negative k times the position x, right? So the left-hand side of our equation here becomes negative k. Oops. It becomes negative k times x. And we say, I can't seem to sit quite properly in my chair today for some reason. And we say that that is equal to the mass of the object multiplied by its acceleration. Now, make sure that we understand, or I don't need to write, we can just call the acceleration a, right? No, I want to call it x, a sub x, for a reason that we'll see in a second. So now notice that there's a negative sign on the left-hand side, positive sign on the right-hand side, and I think that's consistent with what's going on here, because in this case, x would be a positive quantity. If we define this direction to be the positive x direction, right, then x is a positive quantity, but the acceleration is a negative quantity. So that's the relationship here, that x is positive while acceleration is negative. And that'll always be true in systems like this, where you have what's called a restoring force. So how do we analyze this system right here? Well, one thing we can do is we can rewrite it like this. How else can I write the acceleration in the x direction? Is there another way I can write that? Like, what's another way to describe what the acceleration of this object is? How is it related to some of these other things in this equation? Is the acceleration in the x direction in any way related to the coordinate x? Yeah. So it's the second derivative of x with respect to time. Right? It's the second derivative of x with respect to time. Now keep in mind that our whole goal here is this. What is x as a function of time equal to? That's our whole goal here. Is what is x as a function of time equal to? And what we have here is an equation that tells us something about what the function is. It tells us that if you have the function x, and you take the derivative twice with respect to time, you get back the same function. You take the derivative twice, you get the same function back. Plus, you get some other stuff. You get a negative sign and a k over m. What we're going to do is we're going to just say, suppose that we let, we don't have to do this, but it's just for simplicity, k over m be equal to something that we're going to call omega squared. Why we call it that will become immediately apparent. But for now, we're just going to call it omega squared. Okay? That's not w, it's omega. So now our equation basically becomes negative omega squared times x is equal to the second derivative d2x dt2. Right? And now, again, our goal here is out of this equation to figure out what function happens to satisfy this equation. This equation has, it's a type of equation. There's an entire class in mathematics on. Do you guys know what it's called? Certainly some of you guys have seen equations like this before in your math class. Yeah, this is called a differential equation, or a class that's often referred to as just diffeq. It's a differential equation. And I'm sure a lot of you guys haven't taken differential equations, so you think, well, why are we talking about this? Well, the reality is that solving an equation like this, all you really need to know is basic calculus. Differential equation is a name for a type of equation, but it's really just calculus, okay? You guys know what this means, right? You know what second derivative means. So the way you have to think about this is what function x, and you can pick whatever function you want, you can just test things. You can be like, well, what about the function t squared, right? Because it's x is a function of t, right? What about the function t squared? Will that satisfy this? You can check for yourself. If I put in t squared right here, will this work? Let's see. This is how you solve these problems, actually. Yeah, you want to. So let's try x of t equal to t squared. Okay. So what's the first derivative? It's just 2t, right? What's the second derivative? Just 2, right? So now you compare the second derivative, right? You compare it back to this one. Is there any relationship between these two? Not really. Right? If we put it into our equation over here, what we would get is t squared is equal to negative omega squared times 2. And that just doesn't work, right? They're not equal to each other, right? Would you guys agree? Pretty obvious. That 2 times whatever omega squared is not equal to t squared. This is not a true statement, right? So our first try did not work, right? So now you start thinking, okay, I got to be a little more clever than this. Apparently something like t squared isn't just going to naturally solve this. So you think, okay, well, what kind of function would I imagine that when I take the derivative twice, do I get the same function back? And certainly you guys can think of one like that, right? What kind of function, when you take the derivative 2 times, you get exactly the same function back? Can you think of any examples? E to the x. Let's try that. All right, let's try e to the x. So, try x of t. Now, and this is where it has to be a function of t now, right? So we'll try e to the t, right? Now you guys know the 3 lines here, right? X prime derivative is going to be what? Just e to the t, and x double prime of t is obviously e to the t, right? Let's try that. So now our x is e to the t. We'll put that right there. So we'll have negative omega squared e to. Oh, now it's doing this weird stuff. I don't want it to do that. I don't like that. No. Undo, undo, undo. So x is e to the t, right? So you put e to the t right here. And then second derivative is also e to the t. We're closer now. We have the same function on both sides, but unfortunately we still have this omega squared here. How could I get that on this side? What can I do to get that omega squared over here on this side? E to the omega t, right. So here, let's change this. Right? So now we're going to try e to the omega t. The derivative is now going to be omega times e to the omega t. And then the second derivative will be omega squared times e to the omega t. So now we're getting really close, because now our first derivative is now e to the omega t, that's x, and our second derivative also has an omega squared here. Oh, it looks awful. It just looks awful while doing that. Let's just scooch this guy over a little bit, right, and then put the omega squared right here. Okay, now we're close, because both sides have e to the omega t, that's good. Both sides have omega squared, that's good. But unfortunately our equation now says negative 1 is equal to 1, and we know that's not true. We know this doesn't work, right? So what else could we do to get this to work? You guys see a trig function? Yeah, why a trig function? What made you think that? They switch signs. They switch signs, exactly what Via said. Sine and cosine switch signs, that's the key, right? Now I will say, we're going to come back to this one, okay? But, because there is actually a way to still fix this one. I want you guys to think about how we could do it. There actually is a solution. This is really close to, oops. This is really close to a solution right here. There's something that's missing. So our final attempt now will be to try a trig function, and let's use cosine. And actually, there's going to be a reason for us to use cosine that you're going to see here in a second. So now the last one we're going to do is we're going to try x of t is equal to cosine. Can I just do cosine t, or do I need to put something else in here? Exactly. You're going to need the omega, right? And there's going to be something else we can put out here, and there's actually something else we can put in here, but we'll talk about it in a second. So the first derivative now would be negative sine omega t. Negative sine of omega t. And you'd also get an omega out here, right? So let me just erase this and just put the omega in front. Back to black. We're going to have an omega sine omega t here with a negative sign. And then, let's go down just a little bit here. Finally, when we take the derivative again, you'll get negative omega squared cosine of omega t. And now we've got it, right? We put those back in. The left-hand side becomes negative omega squared times cosine omega t. That's what x is. If you guys are all following what we're doing here. And then the right-hand side is going to be automatically negative omega squared. And we found it. We found something that actually satisfies what we call our differential equation. And for those of you that haven't had differential equations before, this is quite literally what you do in that class. You learn methods of ways you can get around just guessing and checking, but largely at the end of the day, you're going to have to make a guess to solve it. But can you guys see, like, boom, we're good. That is at least one possible solution. There's more than one solution to this. That is at least one possible solution to this particular equation. There's more that we got to check, though. One other thing that we have to check is to make sure that this solution that we've gotten actually gives us the coordinate as a function of time. And we need to modify it a little bit to make that work. Is there anything I can do to this function here that would not alter the derivatives? Because the derivatives are perfect now, right? Amplitude. Now, where could I put the amplitude? If I multiply by a constant, that doesn't really change the equation, right? I can drop an a in there, which is our amplitude, and it doesn't really modify the equation. Yeah. So then I'd have an a here, and then this whole thing would be multiplied by a, right? And now, again, we haven't modified this in any way, so we're getting closer. What else could I do to change the function? What else could I do that would not alter what's going on here with these derivatives? Is there anything? What about inside the cosine function? Is there anything I could add inside of here that would not alter in any way what the function happens with the derivative? Can I add a term? What? Yeah, some angle or I can add anything I want inside of the argument of the cosine, and it won't change anything. So we're going to call it phi, and we're going to add that in here, and we'll be completely finished now. So this phi we call the phase constant, and I'll show you what it does here in a second. In the case that I've given you, the phase constant is actually going to be equal to 1. Or sorry, 0. Okay? So now, in general, our general solution now is going to be this. X of t is equal to the amplitude multiplied by the cosine of omega t plus a phase constant. And what that phase constant represents is just where in the motion you start time, basically. So phi is what we call the phase constant. It's really just a shift, right? It's an angle, okay? It's measured in, like, radians, right? That function, if we were to plot it, you guys know exactly what it would look like, right? Whatever, this is fine. So if I want to plot that function, let's say that I let time go on this axis and x go on this axis, then I let this be x equal to a and this be x equal to negative a, then the motion that we're describing now, well, it's basically a cosine function. Now, we need to make sure that at time equal to 0, right, the object has a 0 velocity and has an amplitude that's equal to a, right? What we know is that basically x of 0 has to be equal to a. 0. And we also know that v of 0 has to be equal to what? 0, right? And we also know that the acceleration at time equal to 0, what would that be? What would the acceleration at time equal to 0 be? What could, Wouldn't it be the force divided by the mass? But it needs to be negative. Whoops. It's kx over m, but it needs to be negative. And in this case, the x coordinate at time equal to 0 is a, so it really needs to be negative k over m multiplied by a. Now let's see how we can actually make our function fit this. And I realize now I can't plot it yet until we've done that. How can I check that this stuff is true? All right, so if x of 0 needs to be a, let's look at what that tells us about this equation. If I plug in x of 0, I'm going to get a cosine of phi. And this actually tells me that if I need x of 0 to be equal to the amplitude, right? That's our initial condition. This tells us that basically cosine of phi has to be equal to 1. What does that mean phi is equal to? Let's use radians, by the way. Pi over 2. I don't think so. Cosine of pi over 2 is 0. What does it need to be? 0, right? Or, what else? Negative pi or pi both give you, I think, negative 1, don't they? I think it's 2 pi. I think it's every... It has to be... Yeah. Okay. Alright, so that tells us that phi is 0, right? Okay. Tells us that phi is 0, I think, right? What about velocity? How can we ensure that this one works? How do we figure out how we know for sure that the velocity is 0? What do we know about the velocity? We're at t equals 0, but we gotta... It's this, right? X prime is the same thing as velocity, right? And x double prime is the same thing as acceleration, right? The sign needs to be 0, exactly. So let's check that. This is velocity as a function of time, right? So our velocity is a function of time. Let's check that. What would that be? So v of t... So look, this tells us something, right? We now know that x of t is equal to a times the cosine of omega t, right? That's actually our function. This tells us where the object is. But now we got to check to make sure this actually works. So v of t would be... Oh no. See, I love that it just randomly does that. I wondered... Oh no, what is it even doing? Undo, undo, undo. There we go. Back to draw. Turn off ink to shape, please. V of t is going to be the time derivative of this, which is basically just negative a omega times the sine of omega t. So if I take v of 0, what I'm going to get is sine of 0, so I get 0. That works out just fine, right? Perfect. Velocity at time equal to 0 is 0. What about acceleration? Well, that's going to be this one. And my acceleration as a function of time is now basically the derivative of this guy. The derivative of this guy is going to be equal to negative a omega squared multiplied by sine of omega t, or cosine of omega t. And now, what's a of 0? A of 0 is basically just negative a multiplied by omega squared, because cosine of 0 is 1. But remember that omega squared, remember where that came from before? Where was it? Let k over m be equal to omega squared. So technically what this says is it's negative a times k over m, and I'm pretty sure that that's exactly what we were looking for the acceleration at time equal to 0. That means that this function completely satisfies all the conditions that we placed on the system, right here. Oh man, why you gotta be so bad on the last couple weeks of class? There you go. That perfectly describes the motion as a function of time, and now what we can do is we can draw ourselves a little coordinate system, and we can do exactly what I said. I can say, suppose that I draw a line, let's draw a line right here, draw a pink shape. Just want to draw a line across here, and then I want to basically copy that line equal distance on the other side, down here, and then I'm going to say that line represents, so this is going to be the x direction, this is going to be the t direction, and this line right here represents x equal to positive a, This line right here represents x equal to negative a, and now my function is basically a cosine function that starts up here, it's going to go through some point right here, it's going to go to here, and it's going to go to here, and it's going to go back to here, and it's going to just be a nice cosine function that kind of goes down like this. That is just completely atrociously bad. Easier if I start back here. So it goes up, then it curves back down, and it curves back up like this. Hits a maximum right there. Beautiful. No, it's not on both monitors right now, Summer. I just think like something's wrong. I'd saved like a profile that allowed me to use the buttons that are on the tablet to do things like undo, and it's not working now. So I'm assuming that I got to reset that. And I'll probably try to do it during the break. But that literally represents the motion as a function of time of this object, right? This object that's basically, if you think about it, what's it doing? It's basically, you pull it out to here, right? And then you just go, you let it go, and it goes zoop, 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 back and forth, and back and forth, and back and forth. That's what it does, just back and forth, and it follows this beautiful sine wave thing right here. The rate at which it moves is given by this. Like, you guys learned this probably in your trig class a long time ago when you were analyzing functions, that the bigger that this quantity is right here, the more scrunched up the graph is, right? You might have a graph, like if you double the frequency, for example, your graph is going to be like, it's going to go through 2 cycles in the same amount of time. So it turns out that what that thing that we called omega is basically the angular frequency of the system, okay? That's one of the most important parts about this, is that the quantity omega is equal to the square root of the spring constant divided by the mass, and this is quite literally the angular frequency of the system in radians per second. So it could be, so for example, omega could be equal to like 2 pi radians per second. What that would mean is that it goes through 1 full cycle every second. What's a full cycle? A full cycle would be like, box starts off out here, passes through the middle, and then it goes to the scrunched up point, and then it repeats the process over again. Doing kind of a rough picture here to outline what we're talking about. So then it would go to the middle again, and finally it would repeat by going over to here, okay? That is 1 cycle. Let's scooch this guy a little bit to the left so it doesn't look like that didn't work at all. This is not at all what I wanted to do. I'm just gonna erase this. Just want to kind of copy the first one maybe. That's 1 full cycle, and we can kind of mention some things about it. This is the point when the x-coordinate is equal to a. That's, remember, the maximum position. The velocity is equal to the 0, and the acceleration is at maximum. When it passes through this point right here, oh, and this probably would occur at t equal to 0. When it gets to this point right here, we say x is equal to 0 right here. This is the x equal to 0 coordinate. We call that the equilibrium position, or the unstretched position of the spring. At this position, like we say, x is 0. It's going to be moving in this direction with some velocity. At that point, the velocity is at maximum. I'll tell you what that's equal to in a second here. And its acceleration is now equal to 0 because the spring is unstretched, so there's no force. And then what time does this occur at? This occurs, we'll put the times over here, so this is t equal to 0, right? I'm going to say this is going to occur at a time that's equal to 1/4 of what's called the period, okay? And I'll tell you what the period is. T represents period. It's a periodic motion. And the period, we've used this before, I believe. We talked about, orbits, right? And the period of an orbit, just erase some of this junk. The period for an orbit was the time for one orbit. The period for this is the time for 1 cycle. So I can tell you very quickly here that in terms of the period, this is going to be t over 4. then this third position right here is t over 2. And this fourth position here is, I'll put it right here, like t equal to 3t over 2. And then, no, not 3t over 2. My bad. 3t over 4. And then the final position here is t equal to t. And then you basically go back to the beginning again, right? So it goes here to here, to here, to here, to here, to here, to here. And kind of a sine wave, right? Or cosine wave, right? You can actually see, I'm going to draw a line here. Our cosine wave is basically that's why we say it's a cosine wave, right? Just like that. I'm going to take those off, though, because I think that's confusing. Okay, period is actually related to this quantity here. Since it's the time for one cycle, it turns out that the period is basically, you get it by taking 2 pi divided by omega. So that's equal to the period. And obviously that ultimately is related back to the fundamental constants related to the system, which are the mass and the spring constant, right? Let's finish up our picture over here so we can kind of talk more about this. When the object gets to this point right here, it basically is the opposite of the first position. At this point, the velocity is now equal to 0. X is equal to negative a. Velocity is equal to 0. And the acceleration is now at maximum. Okay, when we get down to this position here, we're going back through the middle again, so now we get velocity in this direction, right? This is v equal to v max. And then other things are the same, so x equal to 0, a equal to 0. Notice that when x is 0, a is also 0. And finally here we get back to what they repeat. X equal to a, v equal to 0, and acceleration equal to maximum. And that's it. That's simple harmonic motion right there. Every form of simple harmonic motion has a pattern like this. And it's a pattern that's repetitive. And we use it to set up clocks, and we use it to create accelerometers. Like your phone has little accelerometers in it that are designed with little, like quite literally an object attached to a spring to pick up when your phone moves and stuff like that. It's quite literally got something inside of it like this, a little tiny box attached to a spring, I believe in between capacitor plates, that reads out voltages and stuff like that the phone can pick up to know when you're moving it, right? So that when you turn your phone from portrait to, like from sideways, like when you rotate your phone, like it knows that you're rotating it, right? And the screen will, that's part of how it does. It's like got a little box on a spring in there that's designed to measure accelerations, and those accelerations that it measures basically flip your screen for you and stuff, right? So it all goes down to something like this. This is at the core of how clocks work. It's the core of how, like, a lot of our understandings of science come from an understanding of things operating like this. We think of atoms as undergoing simple harmonic motion in order to understand the type of radiation they emit. We think of, and that's simple harmonic motion. Do you guys have any questions? Simple harmonic motion is really neat, in my opinion. We'll do some problems, hopefully help you guys understand. But do you guys have any questions at all? Does the picture make sense? Now, what are these maximum velocity and maximum acceleration? Well, if we go back to our velocity as a function of time here, right? What's the maximum value you can get out of this function? Let's start with this piece. What's the maximum value that this can have? Assuming that time is not an imaginary number. It's 1, yeah. So then what's the maximum value the velocity can have? Basically this, right? The thing sitting right in front of the sine function, the maximum velocity is just that. It's a times omega. That's a pretty nice thing to know. So, I'm boxing off all the important equations for you guys here. We now know V max is equal to just a omega. That's a really handy thing to know. We're going to use that to solve some problems. We also know, omega is square root k over m. A max is basically this, right? It's the same reasoning. You look at a as a function of time, you see it's related to a cosine function. So a omega squared is the biggest value that this can be. So the max acceleration is a times omega squared. Now let's look at omega and let's see if we understand something about this. Omega says that the rate at which the object oscillates back and forth, effectively its speed, is given by the square root of the spring constant divided by the mass. Does that make sense to you? What this means is that if you have a really stiff spring that has a large spring constant, think like a spring on your trampoline or something like that, it's so stiff that it forces the system back to equilibrium very quickly. So the oscillation frequency is going to be really high if you have a stiff spring. Also, if the mass is small, the frequency is going to be higher because the force that you get per mass is bigger, or the acceleration you get per mass is bigger. If the mass is large, however, the system's going to be sluggish. It's going to oscillate very slowly back and forth and back and forth. So hopefully this makes sense to you. Bigger mass, slower angular speed. Smaller mass, big angular speed. And then the bigger the spring constant, the bigger the angular speed's going to be. And that's pretty much all you need to know about simple harmonic motion. We're going to do some stuff with energy, but that's the kind of intro to it. Okay? Do you guys have any questions at all? Now, I can either do a problem now and then discuss energy, or yeah, I think that's what I want to do. We're going to do a problem, and then we'll talk about energy afterwards. I'm very reasonably certain that we can do this in about 10 minutes. These problems are quite honestly some of the easiest in all of physics if you truly understand what's going on. Because a lot of what you're going to do here, you may have actually already done in a mathematics course, albeit it could have been a while ago in a trig course or a pre-calc course or something like that, where you're basically analyzing functions like this. In this case, it's x as a function of t, and you may have been doing y as a function of x or something like that, right? So, let's give it a shot. Given that we know that an object is undergoing simple harmonic motion, and its position as a function of time is 4 times the cosine of pi t plus 1/4 pi, with no units in here. I'll write the units in when I rewrite the function. Where x is in meters and t is in seconds. Find the following. We want to find the amplitude of the motion, the angular speed, the period t. We want to find velocity as a function of time and acceleration as a function of time, max velocity, max acceleration. This just means we're not going to do part d, and then part e is delta x. Okay? Should be pretty easy. So let me rewrite the function. So the way I would write this is it's x as a function of time is equal to 4. Now that has to have a unit, right? It can't just be 4, right? But it says x is in meters, so to make it have meters, we say 4 meters, and we multiply this by the cosine of pi t. Well, that pi needs a unit too, so it's basically pi radians per second times t, and then plus pi over 4, and then this is just radians. All this means, in comparison to what we just described, is just the time equal to 0 is not the time when the object is in the same position. So our specific system here was t equal to 0, you start here, by t over 4 you're here, so on and so forth, right? And specifically, these were our initial conditions. V equal to 0, at t equal to 0, x equal to a, at t equal to 0. Well, that's just not true for this system, okay? At t equal to 0, the object is not at 4 meters, the amplitude, right? It's somewhere else. That just kind of just shifts the system in time, that's all it really does. All right, so we want to find a, omega, and t. You guys tell me really quickly, this is not hard at all. What is a equal to? What is the amplitude? It's 4 meters, exactly. It's just that simple. I know for a fact you have homework problems exactly as. What's omega? Remember that our general function for this was x is a function of t, has the form of a cosine, it could be cosine or sine, by the way, it's not important, omega t plus an angle phi. So it's pi, exactly. That right there is omega. Omega is just straight up equal to pi radians per second. Okay? What about the period? Well, period, I said you can find by doing 2 pi divided by omega, right? So the period t is equal to 2 pi divided by pi. We get rid of the radians and just get 0.5. No, not 0.5, 2, right? It's 2 radians per second. Or sorry, 2 seconds is the period. So there's our period. There's our angular frequency, or angular speed sometimes I'll say, and there's our amplitude of 4 meters. Super easy. Okay, next we want to find what v of t is. What's the velocity as a function of time? How do I find that? the derivative, right? So the derivative of this function, so this is going to be dx dt. You know, I should mention it now because sometimes you're going to see this in physics textbooks, those of you that may look ahead or something like this, or you'll also see it in engineering textbooks. There's actually a different way to write dx dt. You do an x, and you put a dot on top of it. That is, we call it x dot, it's the time derivative. And if you want to describe what d2x dt2 is, kind of similar to the way that you guys write like f and then f prime and then f double prime, you just put second derivative, you just put two dots. So this is velocity, this is acceleration. It's just a nice handy notation to use in physics. Larson is letting you down. Who's Larson? Is that a math teacher? No. I think this is more of a physics thing that we use the x dot and x double dot, but my memory historically is this was introduced either by Leibniz or Newton, this type of notation. Anyway, I just mentioned it here. I never use this type of notation in physics, but I'm pretty sure that Dr. Hacking does in his physics classes. I've walked by his classroom and I've seen these type of notation on the board, so you may see that. Anyway, velocity is a function of time. We take the time derivative. This is where derivatives become really powerful. Now we can quite literally find the velocity at any moment in time by just taking the derivative of this function, and that's really powerful. So it's going to be 4 times pi, right? So we're going to have 4 pi. And when you do meters times radians, you kind of just drop the radians. So it's going to be 4 pi meters per second multiplied by, well, there's also going to be a negative sign because it's a cosine function, because when you take the derivative now, it's going to be sine. And then sine of, okay, pi t plus pi over 4. I don't want to write the units every single time, but remember that they're there. So negative 4 pi meters per second. There you go. And then to find the acceleration as a function of time, we would just take the second derivative. Man, it really makes a lot of sense to write it like this, but I'm not going to do it. Is the second time derivative, d2x dt2. And that one's going to be equal to negative. We're going to have a 4 pi squared, because derivative of the inside. And that's going to have units of meters per second squared. And then that is times, back to cosine, right? Cosine of omega t. Oop, not omega, but actually pi. Pi t. It's pi over 4. There we go. I don't want to box them in, but that's the answer to part B. You guys got it? Oh, Stewart is letting you down. The calculus book, Stewart. Gotcha. Yeah. I thought it was a professor. Okay, so C. Vmax and Amax. Well, I just showed you up here. You get Vmax by doing this. You get Amax by doing this, right? We already found omega was right there. Or we can just see from these functions, right? That's Vmax. And that's Amax, right? However you want to do it, basically. But part C, Vmax is basically just whatever 4 pi radians per second is. Something like 12, not radians per second. It's meters per second. This is velocity. And then Amax is 4 pi squared. There you go. This is... I don't even know what this question is about. We're not going to read it. The phase angle... The phase angle is just this. It doesn't change. That's phi. So I don't know what that question is supposed to be. Delta x is... If I want to find delta x of the body between t equal to 0 and t equal to 1 seconds, I basically want to take the x coordinate at 1 second, and I want to subtract from that the x coordinate at 0 seconds. Okay? And that's going to be equal to... I don't want to rewrite all this up. I'm going to go on break real quick here. So basically just plug in x equal to 1 and plug in x equal to 0. And we'll do that just by using calculator. And you guys can feel free to do it yourself too. So plug in x equal to 1, plug in x equal to 0, see what you get, and then yeah. I need this where I can. Okay, so x of 1 would be 4 times. We're in radians. You need to be in radians for most of these problems. 4 times pi times 1 second plus pi over 4. That's the... And we need to... That's x of 1 right there, right? And then we basically just need to subtract x of 0. So we'll just put a 0 in right there. Enter. Boom. negative 5.6. We'll talk about what that means. But that's basically its displacement, right? Did I do this right? Cosine of... I just want to try something. So the value of that is that. And the value of this is this. Ah, okay. So... Oh, and sure, it's half of a cycle, right? Because the period is 2 seconds, so it's half of a cycle. So when I take basically, what was it? This one minus this one, that tells you where it is. It went from negative 2.8 to positive 2.8 in that time. So its displacement is negative 5.66 or whatever. Where's my pen? And what is it? Meters. That's delta x. Right? And since we found what the values of these were, it basically started here at x of 1. We said x of 1 was equal to... Can I not scroll up here? This was x of 1, right? Negative 2.8. So it's at a position... Oh, it's this is final. Oops. Here, we'll do this way. So this is x at time equal to 0, which is positive 2.8. And then this is x of 1, which is equal to negative 2.8. So it basically moved from here back this way, and delta x, we're saying, is negative 5.66. Okay? From here back to there. This is basically, you might think of this as xf, this is x initial, or you can think of it x of 1 and x of 0, however you want to think about it. Does that make sense? Do you guys have any questions? I'm going to stop the stream here and we're going to take a break, but if you guys do have questions, please ask.